Welcome to this explainer. I am so glad you're here today because we are tackling one of the most fundamental, yet honestly, often overlooked aspects of technology. We're looking at the fascinating concept of how hardware acts as a bridge. Think about it for a second. You and I live in a messy, continuous, highly unpredictable physical world, right? But a computer, it operates in a perfectly precise, rigid, discrete digital world. So how do we actually get our physical intentions across that border? How do we talk to the machine? Well, that is exactly what we're going to unlock today. Okay, let's look at our agenda. We'll start with bridging the digital divide, move into manual entry and navigation, then cover digitizing sight and sound, passive sensors and converters, and finally, we'll wrap it all up with the final system blueprint. Section 1. Bridging the digital divide. Humans and computers exist in fundamentally different dimensions. We speak in movements, in voices, and environmental changes, while the machine strictly speaks in ones and zeros. So the solution here is an input device. It's a mandatory hardware bridge. It literally sits right in the middle, capturing a physical event, like you pressing your finger down, and translates that human action into a highly structured format that the central processing unit, or CPU, can actually process and understand. Without this hardware bridge, the computer is completely isolated from the outside world. It'd just be a very expensive paperweight. Section 2. Manual entry and navigation. Let's start with the absolute basics of manual entry. We have the standard keyboard. Now, it is incredibly versatile, perfect for word processors and complex software commands. But the trade-off is that it takes up a ton of desk space and can actually be kind of slow for large data entry. Contrast this with the numeric keypad. It drops the alphabetic input entirely to become highly portable and lightning fast for just entering numbers. This is exactly why you see these at ATMs or checkout terminals for quick PIN entry. You're giving up versatility to gain pure speed and security. Now, what's really interesting about this slide is the hidden mechanical journey of a single keystroke. When you press a key down, you aren't just typing a letter on a screen. You're physically pushing a plunger down to connect a contact leaf, which then completes a circuit on the base membrane. That completion sends a specific electrical signal straight to the CPU, which then rapidly checks an index file to identify exactly which character you meant to type. All of that physical engineering happens in literal milliseconds just to get one single letter to show up. But we have to relate this hardware back to the user, because forcing our physical bodies to interface with these rigid devices definitely has a cost. Using standard flat keyboards over long periods of time introduces a very real physical risk, repetitive strain injury, or RSI. Because our hands aren't naturally meant to just lay perfectly flat for hours on end, ergonomic setups like split keyboards and dedicated wrist supports become absolutely crucial to maintain neutral joint alignment and protect our physical health while we're working in the digital world. Beyond typing, we obviously have to move around our digital space, so let's break down your navigation choices. The classic optical mouse gives you incredibly fast and accurate navigation, but it absolutely requires a flat surface and carries that same RSI risk we were just talking about. The laptop touchpad solves the space issue by being fully portable and built in, but as we all know, trying to do precise drag and drop operations on a touchpad can be remarkably frustrating. And then there's the tracker ball. It has a stationary base, meaning you only move your thumb or your fingers. It requires very limited wrist movement and is absolutely perfect for cramped industrial spaces where a regular mouse just wouldn't work at all. Now, if we want even more direct interaction, we look at the screens themselves. Compare modern touchscreens with outdated legacy light pens. Touchscreens are brilliant because they require absolutely zero training. You just point and tap. That makes them perfectly user-friendly for things like ATMs or self-service kiosks. However, they do get dirty very quickly, and your input options are a bit limited. On the flip side, we have the legacy light pen. This old device actually detected light changes as the electron beam refreshed on those old, bulky CRT monitors. It was an interesting bridge back in the day, but it is totally incompatible with the modern LCD flat screens we all use now. But what if you aren't sitting right at a desk? Sometimes the physical world dictates exactly how we must interact. Remote controls use infrared signals to let us operate equipment from a distance, which is a total game changer if you need to safely control machinery in a hazardous environment. Though, yeah, they are constrained if a thick wall blocks the signal. And for simulations, standard keyboards just fail completely. You cannot simulate steering a car by pressing an arrow key. Joysticks and driving wheels provide natural, continuous physical input, creating a bridge that perfectly mimics real-world physics for racing games and flight simulators. Okay, moving on to Section 3, digitizing sight and sound. Let's move to and see how this builds when we try to digitize a physical page. We go through an amazing three-step journey. First, you take a fragile hard copy document and place it in a scanner. The hardware resolution dictates the quality, creating a static digital image file, like a JPG. But here's the thing. At this stage, the computer just sees a picture of words, not actual text it can understand. This is where optical character recognition, or OCR software, steps in. It analyzes the shapes in that picture and essentially unlocks the image, translating those visual shapes back into a fully editable text document. It's like an incredible hardware-to-software relay race. We do the exact same thing with our senses. Digital cameras eliminate the need for physical film entirely, storing media on removable SD memory cards and letting you do instant on-device editing. Meanwhile, microphones act as the bridge for our voices. They convert physical sound waves in the air into electrical current and then into a digital format. This is literally what makes VoIP, or digital conferencing, possible. But it's definitely not perfect. Speech-to-text software relies heavily on this input, and it frequently runs into the homophone challenge. Struggling to differentiate between words that sound identical, like there with an EIR and there with an ERE.
Section 4. Passive sensors and converters.
To really understand passive sensors, we first have to recognize a stark contrast. In our physical environment, data is analog. Heat, light, sound, they all occur in continuous flowing waves. You don't just jump instantly from freezing cold to boiling hot. It's a smooth transition. But inside the digital computer system, data is discrete. It only understands distinct, rigid blocks of ones and zeros. A sensor's entire job is to read those continuous analog waves from the environment without any human interaction whatsoever. So the crucial point is that a sensor alone isn't enough, because the sensor picks up an analog wave, and the computer only reads digital ones and zeros. You need an intermediary. Enter the ADC, the analog to digital converter. This is the absolute ultimate translator. It is the mandatory bridge for all continuous sensor data, taking the physical world's flowing waves and chopping them into discrete digital blocks that the CPU can finally read and react to. And this brilliantly illustrates that exact path. You have continuous physical waves like ambient heat or sunlight hitting a sensor, but it can't go straight to the CPU. The data must cross the structural processor, the ADC bridge. The ADC basically ingests that continuous wave, cleanly converts it into binary code, and hands it straight over to the computer for processing. It's just a beautifully seamless relay going on in the background all the time. Once you understand that ADC bridge, an incredibly diverse ecosystem of sensors opens up. You've got temperature sensors regulating our washing machines, while pressure sensors serve as invisible tripwires and intruder alarms. You have light sensors automatically bringing streetlights to life at dusk, and acoustic sensors listening for liquid flow deep inside industrial pipes. Even chemical processes rely on constant, invisible pH monitoring to keep our environment safe. All of this happens completely invisibly, continuously translating our world into actionable data. Finally, Section 5, the final system blueprint. Let's put you in the driver's seat for a second with a rapid-fire diagnostic matrix to test what we've learned. Which device perfectly solves specific real-world scenarios? If you need to enter a PIN securely at a checkout, what do you use? You need the numeric keypad for speed and a low space footprint. What if you're navigating control software in a highly cramped, dirty factory? You completely ditch the mouse and use the stationary tracker ball. And if your scenario is digitizing and archiving fragile, historical books, you use the 1-2 punch of a scanner combined with OCR software to pull it directly into the digital realm. It's all about picking the right bridge for the right gap. This grand architecture really summarizes our entire journey today. Whether it's our active manual entry via keyboards and touchpads, media capture pulling in sight and sound, or environmental sensors feeding continuous data through the ADC, every single one of these pathways funnels directly into the center, the digital processing CPU. It's an incredible, intricate web of hardware ensuring the digital brain is constantly connected to our physical reality. Which leaves us with this final thought. We've seen how we actively force input data, but we've also seen how effortlessly sensors pull data from the world without us doing a single thing. As these hardware bridges shrink and passive sensors increasingly surround us in our homes, our cars, and our cities, what happens to our physical privacy when the translation into digital data becomes completely invisible? It is a fascinating and frankly crucial question for the future of human-computer interaction. I want to thank you so much for joining me in this structured explainer today. Keep learning, keep questioning, and I'll catch you next time.